He was talking about impossibility results in mechanism design.
Okay, so what I want to do today is to talk about something that I've been working on for some time, and I want to give you like a quick survey of where we stand. So we're going to talk about proving impossibility result in algorithmic mechanism design. Specifically, we're going to talk about two different settings. I'm going to show you two different approaches to prove two different impossibility results. So this first setting is going to be a multi-Aint auction. And in this setting, we're going to use the characterize and optimize approach to prove an impossibility result. And the second one is going to be combinatorial auctions with some other bidders. And in this setting, we're going to use the direct hardness approach in order to prove an impossibility result. All right. So most of this talk we're going to spend on the second setting, combinatorial auctions with some other bidders. So what I want to do now is to formally define this setting, and then formally define the setting. Then I'm going to talk about it a bit more. All right. So combinatorial auctions. We have n bidders, m different items. Items might be complements or substitutes. So items might be complements or substitutes. And to capture that, each bidder I has a valuation function vi. So vis denotes the value of bidder I for the bundle of s items. The vi might be quite a large object. In the worst case, we might need to specify a value for each one of the possible 2 to the m bundles. So we're going to assume in this talk that these valuation functions are given to us by a black box that we can query via a very simple way. What is your value for the bundle S, or what is your value for the bundle S prime? We're going to make 3 assumptions about the valuation functions. 2 of them are standard. One of them is setting specific. So the first one is going to be that the valuation function is normalized. So the empty bundle has a value of 0. And the second one is that the valuation function is monotone, so adding more items cannot decrease the value of the bundle, the big bundle. And the third one is the static specific one, and it's going to be that the function is submodular, which basically means that the valuation function exhibits decreasing marginal utilities. Actually, in none of the proofs that I'm going to show today, we're going to use this submodularity, so I'm going to skip reading the formal requirement. I guess most of you are anyway familiar with it. Our goal in this talk is going to be to find a location of the items, S1 to Sn, that maximizes the welfare, which is simply, yeah.
You said you won't use submodularity? You mean the theorem doesn't need submodularity?
The proof that I'm going to show you, the specific parts that I'm going to show you, does not use the paper. You know, the paper, the full proof, of course, uses submodularity. Yeah. Yeah. All right. So we want to maximize the welfare, the sum of the values of the bidders. Okay. So this is the setting. All right. So we want to develop good auctions, and this talk I'm going to sometimes use the term algorithm or mechanism to denote the same thing. So what does it mean that we have a good auction? So first thing that we want is the auction to run fast. Just because I'm a computer scientist. So we want the auction to run in time that is polynomial in n, the number of bidders, and m, the number of items. And like, of course, it's very easy to construct fast algorithms that are not very useful, like the algorithm that never allocates any items. So we want to add some usefulness requirement. And this is going to be, in this talk, the requirement that the algorithm is going to provide a good approximation, meaning that you want to find a solution that is within, say, a constant factor of the value of the optimal solution. All right? And we know how to do that. There is a 1.58 approximation algorithm for this problem. So we can always find a solution that is within a factor of 1.58 of the value of the optimal solution. The problem is that, we're talking about an auction setting, so naturally we want to somehow handle the incentives of the bidders. So let's add some requirement to do that. In this talk, it's going to be the talk that the algorithm is truthful. And I'm going to talk only about the simplest type of truthfulness, deterministic truthfulness, meaning private values, and I'll be looking for dominant strategies equilibrium. And we have the VCG mechanism that is truthful and provides an approximation ratio of 1, always gives us the optimal solution. We'll talk about the VCG mechanism in a few slides, but we all know that it is not computationally efficient. So what we actually want to do in this talk is to understand if there is something in the intersection of all these three circles. If there is something that is both fast, provides a good approximation, and truthful. And this is like the main question of this talk. All right? Okay. So what do we know about this problem? It was introduced by Lehman, and Nissan, and they showed that there is a non-truthful greedy algorithm that provides an approximation ratio of 2. And this ratio was later improved to 1.58, and this is basically the best thing that you can hope to do in polynomial time. So from a pure computational point of view, completely ignoring incentives, this problem is well understood. As far as incentives are constrained, we have basically only this result that said that there is a square root of n approximation ratio, and this is quite a poor approximation ratio. And what we want to understand is whether this simple algorithm that we're going to see in a second is optimal or not. And the point is that we don't have, in general, we don't have at all any methods of proving such impossibility result. We don't know if we don't know how to prove if this algorithm is tight or give any lower bound to the approximation ratio of truthful polynomial time algorithm. And what we want to do is to develop like tools and techniques to do exactly that. All right, and let me just say that this situation in which we completely understand the problem from a computational point of view, but we understand very little from truthfulness point of view, is similar essentially to all auction domains that we know. And again, this is like a representative case for that. All right. So what we're going to do next is I'm going to show you, to briefly show you the polynomial time square root of n approximation mechanism. And the first starting point is going to be the VCG mechanism that you all know. It's quite a general mechanism. Let's quickly go over it. I'm actually going to present it in quite a weird way in the sense that the bidders are going to get some items, and the auctioneer is also going to pay for them. This is just to make the proofs a little bit easier. We can fix that if you add the right normalization constant. So what is the VCG mechanism applied to combinatorial auctions? Let's find the optimal location, O1 to ON. So bidder 1 get a bundle O1, bidder 2 get a bundle O2, and so on. We assign the bidders the items accordingly. And then we pay each bidder I the sum of the value of all the bidders in that optimal location. So why do we get a truthful algorithm? This follows from the simple observation that the profit of each bidder simply equals to the welfare of the allocation that we obtain. So to see that, let's consider, for example, bidder 1. His profit is composed of two terms. The first one is the bundle that he got, O1. So he gets a profit of V1, O1 from there. The second one is the payment that he got from the auctioneer, the sum of the values of all other bidders. So sum these two terms together, and you get that the profit of each bidder equals to the welfare of the allocation to be obtained. So what can bidder 1 do? Bidder 1 can try to manipulate, can try to misreport his valuation. The only thing that will happen is that he might cause the allocation to change to one that is suboptimal, so his profit can only decrease. And this is why the VCG mechanism is truthful. Right, good. So great mechanism. The only problem, at least as far as we are concerned, is that it does not run in polynomial time. We have to find the optimal solution for that. So, first naive idea is we have a 1.58 approximation algorithm. Let's use this approximation algorithm, allocate accordingly, and then use the ID behind the VCG payments. Let's pay each bidder the sum of the values of all other bidders in the approximate solution. Unfortunately, we know that this does not work. To be more specific, this works only if the algorithm is maximal in range. So what is a maximal in range algorithm? So it's the following type of algorithms. We a priori select a subset of the range, some pre-selected set of allocation, but fully optimize over this restricted set. Let's see an example that will hopefully clarify the definition that I guess half of you can't see. And this will also be the example that will provide us the square root of n approximation. So we choose the welfare maximizing allocation where either each bidder is allocated most one item or one bidder is allocated all items. So why is it a maximizing range algorithm? By definition, the set of allocation, the set of pre-selected allocations that we have is one where either each bidder is allocated at most one item or one bidder is allocated all items. And the algorithm just chooses the welfare maximizing allocation among this set. So this is a maximizing range algorithm. And we immediately have that this algorithm is truthful. How? We can use the ID behind the VCG payments. We're going to pay each bidder the sum of the values of the others in the allocations that we obtain. So just as before, the profit of each bidder equals to the welfare of the allocations we obtain. What can a bidder do? A bidder can try to manipulate, can try to misreport his valuation, and it might indeed cause the allocation to change, but it is going to cause it to change to one that is suboptimal in the range, so his profit can only decrease. And this is why we have that this algorithm is truthful. It's also quite easy to show that this algorithm runs in polynomial time, and that it guarantees an approximation ratio of square root of m, but I'm going to skip it for now. Questions so far? Good. All right, the obvious question now is whether we can do better. Perhaps we can pre-select more intelligently a set of locations and optimize over this set in polynomial time. And turns out that no. We know that every maximizing range algorithm that provides a substantially better approximation ratio does not run in polynomial time. So the next thing that we want to do is to use the characterize and optimize approach in order to take this limited result, this limited lower bound on a specific type of truthful algorithm, and make it old for every truthful algorithm. All right, so we're going to use the characterize and optimize approach. Now, this is essentially, up until very recently, the only way we knew for proving impossibility results. But we didn't know how to use this approach in order to prove an impossibility result in auction domains. And what I want to do now is to show you why we failed in proving impossibility results in auction domains and a possible fix for this problem. All right? Okay, so I actually don't know how to prove an impossibility result for combinatorial auctions using the characterize and optimize approach. I know to do that for a related setting of multi-unit auctions, which is basically the setting where all items have, in which all items are identical. The formal definition is not very important for this talk. You just have to remember that the situation is very similar to the one that we have in combinatorial auction. So we completely understand this problem from a computational point of view. That is, there is a 1 plus epsilon approximation algorithm for this problem. And the best polynomial time truthful mechanism that we have is a maximizing range one, and it provides an approximation ratio of 2. And again, we don't know whether this algorithm is tight or not. All right, so now we can continue, start doing the characterize and optimize approach. So here is a conjecture that we do not know how to prove. And this conjecture said that every truthful mechanism for multi-unit auctions with an approximation ratio that is better than 2 is actually a maximizing range one, a variant of it. So this is the first conjecture. In other words, the wall looks like that. So the blue circle denote all algorithms that provide an approximation ratio better than 2, not necessarily ones that run in polynomial time. The yellow circle denotes all truthful algorithms, and the conjectured characterization said that everything in the intersection of these two circles is a maximizing range algorithm. And of course, we have maximizing range algorithms that are not maximizing range. All right, so this is a conjecture. Now we have a theorem that we do know how to prove, which is quite similar in the statement to the previous one that we saw in the previous slide. So every polynomial time weighted maximizing range algorithm for multi-unit auctions has an approximation ratio of at least 2. So if we knew how to prove this conjecture, together we had an impossibility result. So start with an algorithm that provides an approximation ratio better than 2, a truthful one. By the conjecture characterization, it must be a maximizing range one, and maximizing range algorithms cannot run in polynomial time. All right? So, but the problem is, of course, that we do not know how to prove this conjecture. We know how to prove special cases of it, prove it under some restrictions, and there are like several attempts to prove that, dating back maybe to 2003, Levin and Nissan. But turns out that one reason for our inability to prove this conjecture is that it's just it's not the right conjecture. So we were quite surprised recently to find a counterexample for this conjecture. Turns out that there is another family of mechanism that we named triage auctions, and triage auctions are truthful. They are not maximal in range, and they provide an approximation ratio of 1.01. So we cannot hope to prove the conjecture trivialization. I'm not going to show the definition of triage auction. It's just, I mean, it's not a very intuitive class, and I think that we don't understand it enough. So I'm going to skip the definition, but at least once we have this, we found this counterexample, we were able to develop the right tools in order to characterize this set of mechanisms quite differently from different approaches that used mainly things like Robert theorem. And we were able to prove that every scalable two-bidder truthful algorithm with an approximation ratio better than 2 is almost a triage auction. Now, the almost here is not very important for this talk, so I'm not going to talk about it. Scalable is the property where if you multiply all valuations by the same number, then the allocation does not change. So, so this is that. In other words, the world essentially looked like that. The dissection of the set of truthful mechanisms and one that provides a good approximation ratio consists of only triage auctions, and some triage auctions are maximal in range. All right, so this is essentially how the world looked like. Good. Now we only have to have an optimization theorem in order to completely characterize an optimized approach. This was very easy, just tweaking a little bit the previous optimization theorem that we had for the maximal in range case to hold for the triage auction case. And we have that no polynomial time scalable mechanism provides an approximation ratio better than 2. Yeah. Multi-unit auctions. Multi-unit auctions. Yeah, I'll talk about it in a second. All right, and this is finally gives us some possibility result for an auction domain, something that we wanted to do for a long time. The main ingredients are, again, we figure out what the right conjecture is. There are triage auctions in the world. And the second one is that we develop the right tools to characterize this set of mechanisms. All right. Now, I started talking about combinatorial auctions with some other bidders. So can we characterize all mechanisms that provide an approximation ratio, a constant approximation ratio, and completely characterize an optimized approach? Maybe we can do that, but that seems quite hard. There is a good chance that it's possible to characterize all truthful mechanisms that provide an approximation ratio better than 2. But we know that if we let the approximation ratio to be like 2.1, 2 plus epsilon, whatever, then suddenly there are many truthful mechanisms that are not maximal in range and they are not triage auctions. And you know, we do not even have a good conjecture of how this set of algorithms look like. So this does not seem to be very promising. What I want to do next is actually to show an alternative for the characterized and optimized approach. It's a new direct address approach. And the main feature of this approach is that we're going to completely skip this characterization step that we do not know how to do, and we're going to still get some impossibility result. All right. Okay. So we're going to prove that this simple algorithm that that I showed you before, this Karlin approximation ratio, is actually tight. We cannot have any better algorithm that uses only value queries. And the starting point of this approach is going to be the well-known taxation principle that says that we can think of a truthful mechanism in the following way. So consider some bidder I and fix the valuations of all other bidders. Now, this bidder I is presented with a menu. And the menu is basically just the list of all possible bundles, and for each possible bundle we put a price. And we know that the truthful algorithm must assign the bidder is most profitable bundle. All right. So it's just like the bidder is going to a restaurant, he gets a menu where near each possible bundle he has a price, and the truthful algorithm must assign this bundle to bidder I. All right, so this is going to be the starting point. And the main idea in the proof is to show that in every truthful algorithm with a good approximation ratio, there is an instance where exponentially many value queries are needed to find the profit maximizing bundle of at least one bidder. So the algorithm must find the profit maximizing bundle of each bidder, and this task is hard More specifically, we're going to have the following two lemmas. The first one is going to say that in every truthful algorithm that provides a good approximation ratio, there exists an instance in which at least one bidder faces an exponentially big menu. This is like, a must. If the menu is very small, then it's obviously going to be very easy to find the profit maximizing bundle. The second lemma is going to say that the number of value queries needed to find the profit maximizing bundle in the menu equals exactly to its size. So in other words, at least one bidder faces exponentially big menu, and optimizing over this exponentially big menu requires making exponentially many value queries. All right? Yep.
So an obvious thing to say here would be if you had demand queries instead of value queries, this would be one query.
Not necessarily. The menu is not guaranteed to be to have additive prices, right? The menu can be actually quite complicated, and it is like in most truthful mechanisms.
What do you mean?
In a demand query, you give a price per item, and then you get the bundle.
Why do you give a price per item?
So that's not a demand query. If you're going to give a price for each bundle, that's not a demand query. And
That is a demand query. You have a price per each bundle?
not under the standard definition anyway. And in any ways, this would require you to specify exponential number of bundles, so it's not going to be computationally efficient. Okay? Yeah. So we have these two lemmas. So in other words, one bidder faces exponentially big menu, and optimizing over this exponentially big menu requires exponentially many value queries. Yeah.
For the lemma, what do you mean, like the menu has to be represented by exponentially number of bits, or like it just have price for exponentially many?
There are exponentially many bundles where in which the price is not infinity.
Right, but then there might be small representation of the menu.
That's absolutely correct. We do not know how to handle that at that point, but still, maybe something like demand queries may help you in doing that. For the simple setting of value queries, this would be enough. All right. The first lemma is actually just an easy application of the probabilistic method, so I'm going to skip the proof of it. The second lemma, I'm going to show the proof of the second lemma. All right, so I want to show that the number of value queries needed to find the profit maximizing bundle in a menu equals to its size. So suppose a bidder is going to a restaurant in which, say the price for the bundle that contains the fries is $10, the price of the bundle that contains the Coke is 20, and so on and so forth. Now consider the following valuation of bidder I. We construct the following valuation of bidder I where the value of bidder I for each bundle equals exactly to his value So the value of bidder I in this valuation equals exactly to the the price of this bundle in the menu. In other words, the bundle that contains the fries as a price of 10, the one that contains the Coke as a value of 20, the bundle that contains all items as a value of 87. So the profit of each bundle for that menu is exactly 0. All right. Now suppose that we slightly change the valuation of bidder I, and we give him a slight bonus for some arbitrary bundle, say to the bundle that contains the fries and the Coke. By the taxation principle, any truthful algorithm must assign this specific item to bidder I. Right? And that would be still the case if you give this bonus to the bundle that contains the fries or to any other bundle. The point is that if you just give bonus to some arbitrary bundle, and if all the access that we have is via value queries, it's going to be impossible to find this profit. If you just query some arbitrary bundle and this does not happen to be the bundle that got the bonus, then you have to continue querying this. You have to continue querying this valuation repeatedly until you find the bundle that you got a bonus. Essentially meaning that you have to query all bundles in that menu, right? Good. Yeah. So that's exactly where I I mean, okay, so most of the work in the paper is actually to make sure that we can construct such a submodular function for which it's hard to optimize, and this is exactly, like, I'm skipping the hard part actually in this proof. Exactly, yeah. No, we're not assuming that. Given an arbitrary menu, we show that there is some submodular evaluation in which it's hard to optimize. This is exactly where most of the work is done. All right, but this is the basic idea. If you just give a bonus to some arbitrary bundle, then you're not going to be able to find the bundle to get profit.
Shahar, but this you choose the valuation of bidder I after you have the value, the menu for bidder I, which depends on the valuations of the other players. So could it be that, I mean, so your lower bound that you need an exponential menu needs to also work in an adaptive manner in some sense?
It does work in an adaptive manner.
Okay, so but you need to state it, so you didn't state it in an adaptive manner in the first one.
I didn't say anything about non-adaptivity or adaptivity. Like, the value queries model allows you to query.
Because the menu depends on the values of the other guy.
Right.
So it could be that, you know, you ask one query of one guy, that immediately reduces the menu for the second guy to be polynomial size.
Yeah, definitely. Still.
Then once you start answering the first query in a way that will continue the lower bound, that immediately reduces the menu of the first guy.
It still holds. Everything still works. Like, yeah, it still holds for yeah, definitely that's a possibility. The proof still works for adaptive mechanisms. The menu is given to us, like, you know, and yeah, we just show that this cannot happen. All right. What's that? What's the question? All right, and again, most of the work we still have to do is to make sure that, you know, this construction, as pointed out, does not work as is. We need to make sure that the evaluation function is modular, and we do that in the paper. All right, let's quickly summarize what we have. So we talked about two different approaches to proving a possibility result. The first one was the characterized and optimized approach, where we discussed the I told you a bit about maximizing range algorithms and why our attempt to characterize all approximation algorithms that provide a truthful algorithm provide a good approximation ratio failed because of triage auction. And then I told you that we can actually characterize triage auction. Then we continued to prove a direct hardness approach. And let me say that our understanding of both approaches is still quite partial. In particular, we do not know how to prove an impossibility result for multi-unit auctions using the direct hardness approach, and we don't know how to prove a lower bound for combinatorial auctions using the characterized and optimized approach. Other things to do, direct hardness for other types of queries, like demand queries, other types of truthfulness, including randomized truthfulness. We do some of it in the paper. And of course, characterizing other problems. I mean, proving lower bounds for other problems. Characterizations are also interesting, regardless if we have like computational applications for them or not. It's good to understand if we have a good characterization. What characterization do we have? And one message of this talk is that there are actually things that we can do that are not just maximizing range, that are not just VCGs. There are interesting mechanisms like triage auctions that are doing something useful. So maybe we couldn't use this particular set of algorithms, but maybe other families of mechanisms exist and they're useful, if not for welfare maximizing, so maybe for revenue maximizing, or maybe for fairness or whatever. So there are still lots of things out there. That's it. Thank you.
Take one question while Jason's setting up.
Yeah. Lisa? Yeah, we don't know how to remove this scalability assumption. Let me just say that what you're saying is true for single parameter domains. For multi-parameters domains, these scales this kind of rounding just felt a bit truthful. So I don't know if any example, let's let's put it like interesting example of a truthful mechanism for a multi-parameter domain where scalability is this running works. So yeah.
Do you know any trials mechanism that work for two bidders when you don't allocate a legend?
No,
For
I
three bidders
mean,
when you don't allocate a legend?
no, you need to.
You always need to not allocate a legend.
If you have to allocate all items, then you got the maximum range algorithm.
Okay, we should actually get started. So thanks again, Shahar.